Hello! Today I'm going to talk about Aristarchus of Samos. Previously we talked about the movement of the sky. We didn't make any real measurements or judgments, we just observed what the sky did. So we determined that the sky appears to be like a celestial sphere that rotates in about 1 day around the Earth, and the axis of that rotation is tilted equal to your latitude. So if you live at 30 degrees north latitude, you would find that axis is tilted by 30 degrees, which means if you look to the north, being a little north hemisphere centric in this class, if you look to the north, you would see the celestial pole in the north hemisphere, pretty much where Polaris is, about equal to your latitude above the horizon. So if you live at 30 degrees, it would be 30 degrees above the horizon. Of course, if you're in the southern hemisphere, the southern pole is going to be raised up, but there's no convenient star there to tell you where it is. But nevertheless, that's what it appears, a sphere rotating around. That sphere carries with it the sun, the moon, and the stars, and some wandering stars called planetae or planets. We also discussed that it takes 1 day for the sun to make one rotation, but the moon appears to go a little slower, and each day it loses about 13 degrees behind the sun. But if we could see the stars and see where the sun is among the stars, we would notice that the stars rotate just a little faster than the sun, getting about a degree ahead of the sun each day. And the planets, the 5 planets that were visible in the ancient times, the outer planets, or the superior planets, such as Mars, Jupiter, and Saturn, they go all the way around the sky with the stars, but they move just a little bit slower than the stars, moving among the stars just a little bit to the east each day, just not as slow as the sun does. And that Mercury and Venus never actually get very far from the sun. Mercury stays pretty close to the sun and cycles between the evening and morning sky fairly rapidly in about 120 days, where Venus gets further from the sun and much brighter and takes almost 2 years to make one complete cycle. It spends about 9 months in the evening sky, then 9 months in the morning sky, cycling back and forth. And those are the inferior planets that go between the sun and the Earth. And we also notice that the superior planets, particularly Mars, when they are in the sky approaching the point where they're opposite to the sun, they are going east among the stars each night, but then they stop and move west. During the middle of that westward movement, which we call retrograde, they reach their brightest point. Mars gets very, very bright. And then they move a little west among the stars, stop again, and move east again, going in their prograde motion. Jupiter and Saturn do the same thing, but just not as dramatically as Mars does. And we also discussed that as Mars moves a little bit to the west each night, staying pretty much with the stars, but not quite as fast as the stars, it moves a little west each night and eventually gets closer and closer to the sun, where it gets dimmer and dimmer and eventually disappears into the sun's glare. So that's just some quick observations. You might want to review that video just to review all the observations we made about the motion of the sun, moon, and the stars and planets. So today we're going to talk about the ancient Greek astronomer Aristarchus, who in around 280 BC started doing some calculations and figuring out what our universe was doing. So I'm not sure what order he did these calculations in, so I want to start with one observation, and that's something that everyone would have observed looking at solar eclipses. So what's a solar eclipse? Well, they figured that out pretty easily because the sun would turn dark. Now, a total eclipse is kind of a rare event in any particular place on the Earth. They happen actually quite often, but you have to be in just the right place to see the sun completely blocked out. But even when it's only partially blocked out, they were able to figure out that, hey, this is happening about the time the moon and the sun are coming together. So the moon must be going in front of the sun. So therefore, a solar eclipse is when the moon blocks the sun. So what's that tell us? It tells us that the moon is closer than the sun, because if we have the Earth here, I'm just going to draw that as a flat line now because there's something else we need to figure out. We have a flat line we're making as the Earth, and we have the sun up here, and the sun gets darkened because the moon, well, it's going the other way compared to the sun. Remember, the moon is going around the Earth slower than the sun, so it's going to be compared to the sun going this way, and eventually gets in front of the sun. Therefore, the moon is closer than the sun, right? And it just so happens that the sun and the moon in the sky are the same size. So we have the sun with an angular diameter of 1/2 degree, and lo and behold, the moon also has an angular diameter of about 1/2 degree. Sometimes a little less, sometimes more. So sometimes when the moon moves in front of the sun, it's not big enough to completely cover it. We call that an annular eclipse. Other times it's larger than the sun and does completely cover it. So sometimes it's closer or further away or something. Sometimes it's bigger, sometimes smaller, but on average it's the same size as the sun. So if the moon is closer than the sun and they look the same size, that means that the sun, being further away, must be larger. So the sun, here we are on the earth looking at them, and here's a 1/2 degree angle across the moon. And so we don't know how far away the sun is. It could be there, or it could be there, or further. But notice the further away it is, the bigger it must be to be the same size in the sky. So there's one thing we learned from a solar eclipse, is that the moon is closer than the sun. Therefore, the sun, being the same size in the sky, must be larger than the moon. Now let's look at lunar eclipses. And the ancient astronomers learned a couple of interesting things from those. One is what causes a lunar eclipse. Well, the moon doesn't completely get blocked or anything, it just gets very, very dark. So could that be a shadow falling on it? The other thing is, they weren't dumb. They were looking at the alignment and they said, this moon is getting dark when it's exactly in the opposite side of the sky as the sun. So if we draw a diagram here, there's the Earth and there's the sun there. Now I just drew the sun bigger than the Earth. We know the sun is bigger than the Earth because in a lunar eclipse, we see the dark part of the Earth's shadow making a triangle or a cone in that shape. Let's say the sun was smaller than the Earth. So let's put them like this. Here is the Earth. Let's make the Earth bigger. Here's the Earth and here's the sun. Okay, so if we are behind the Earth where we cannot see any of the sun, we would be somewhere. If I draw the angles right here, I'm going to draw an angle like that and an angle like that. So anywhere in here we can't see any of the sun. And so that's the dark part of the Earth's shadow. And notice it gets bigger as we get further from the Earth. But that's not the case. The Earth's shadow, let's redraw this, gets smaller as we go into space. Therefore, the sun must be bigger than the Earth. Now, we don't know how big. It could be, let's draw that triangle again. This time it's the Earth causing the shadow here, but the sun could be that big in there, or it could be that big there. We don't know how far away it is, but we do know it's bigger than the Earth. And we also know, because the diameter of the sun is 1/2 degree, across the sky, the angular diameter, we know that the angle of this cone is 1/2 degree. So that's a 1/2 degree angle because the sun is 1/2 degree in the sky. So we know the sun is bigger than the Earth. How much bigger, we don't know yet. But we do know that it is bigger because of the shape of the Earth's shadow. And another thing they learned from lunar eclipses, let's take a look at the moon during a lunar eclipse. Okay, it is shortly after sunset. We're looking on the eastern horizon. There's the moon. So the moon is moving this direction into the Earth's shadow. And the Earth's shadow is a curve across the moon. When we look at this, we look at our position on the Earth. I'll just make it a flat line there for now. There's us on the Earth. The sun is over here. The moon is over here, and the shadow of the Earth is falling on the moon, and it's round. Okay, now let's move the sun to here. Now our eclipse is happening around midnight. So the angle across the Earth is at a 90-degree angle then to a sunset eclipse. And the shadow on the moon Well, let's draw it the right way. The shadow on the moon is still a circle. And they observed many of these over many years and pretty much determined that the shadow of the Earth is a circle this big, and the moon is smaller, and the moon goes into the shadow. But no matter where it goes into the shadow, just drawing the moon going across the Earth's shadow, that shadow, no matter what the geometry, is always circular. So, they weren't dumb. What did they figure out from that? Well, there's only one shape that will cast a circular shadow no matter what the angle of the lighting is, and that is a sphere. So 1,000 years BC, they knew that the Earth was a sphere, and they also knew it was just hanging in space because there was no shadow of a pedestal or anything holding the Earth up. So now we know the Earth is just a sphere. So they knew this a long time ago. There's a myth that is still propagated in the schools today that people in Columbus's time thought the Earth was flat, and that if Columbus tried to sail to America, that he would fall off the edge of the Earth. That was total myth. It was written by Washington Irving. People knew the Earth was a sphere. Very, very ancient knowledge, actually. And wasn't challenged until, guess who? Washington Irving wrote his book about Columbus. Even Ptolemy's atrocious model of the universe had a spherical Earth. So, what did we learn from a lunar eclipse? 1, the sun is bigger than the Earth. 2, the Earth is a sphere. That's pretty much common knowledge. Any scholar knew that. Maybe uneducated people might think something different, but scholars knew that the Earth was a sphere and that the sun was bigger than the Earth. Now let's get on to Aristarchus, who was the first person credited with making some of these measurements and making some observations I'm going to talk about. I think he just got his name in print and got famous for it. I think some of these things may have been figured out long before Aristarchus, but he got his name in print, he gets the credit, so we're going to talk about Aristarchus of Samos. And his philosophy was, it did not make sense for the sun to go around the Earth if the sun was bigger than the Earth. They knew the sun was bigger. How much bigger? They had no idea, but they knew it was bigger. So he said, I believe that the sun is stationary and it's the Earth rotating in the opposite direction. And as I mentioned before, this is not something that was revolutionary. This argument had gone on for quite some time as to whether the heavens went around the Earth or the Earth rotated. But Aristarchus said it's the Earth that rotates and the sun is stationary. So now, thank you, Aristarchus, we now have a spherical Earth that is rotating with a sun somewhere out there, bigger than the Earth, don't know how much bigger, but this is stationary, at least as far as we care at this point, and it's the Earth that is rotating in the opposite direction that is making it appear that the sun is moving. So now, what's the next thing he gave us? Well, like I said, everyone knew the sun was bigger than the moon and further away. How much further away? And Aristarchus figured that out. Once again, this is something that's not rocket science, if you will, and I wouldn't be surprised if other people had figured it out before Aristarchus did, but he gets the credit. So how did Aristarchus figure out the distance to the sun? So let's take a look at some geometry here. Let's put the Earth here, and let's put the sun over here. I'm going to make the sun smaller just for convenience. Now we have the moon. The moon is orbiting around the Earth. So Aristarchus accepted that the moon went around the Earth, or at least for these measurements he did. Now when the moon is orbiting the Earth, what do we see? We see phases. So when it's close to the sun, we see this really thin phase. As it gets further from the sun, that gets thicker, and further from the sun, it gets even thicker. Eventually, the moon gets up to where it's in the south, and the moon is shaped like that. And then it starts getting shaped more like that, and then gets closer and closer to a sphere before it eventually becomes a full moon. So what are we looking at? Well, it's not hard to figure out, they weren't dumb, that the moon is a ball being lit up by the sun. And they knew that it was being lit by the sun because when there's an eclipse, the Earth's shadow falls on the moon gets dark. So the moon's light comes from the sun, they knew this. And what they figured out was, if you look at this picture of this ball here being lit from the right, notice that half the ball is lit up. So what I'm going to point out here, let's draw a picture of a sphere. Well, a circle, because I can't do a sphere on a whiteboard. And we have the sun off in the distance, and I'll just put it here, but the light coming from the sun is going to be falling on it. Rays are pretty much parallel, so the sun is pretty far away, and so half of this ball is lit up. So half of it is dark, and half of it is lit. What does that look like? That looks like when we can see a half moon in the sky. Technically, that's called a quarter moon. So I'll refer to this as a quarter moon, but it's when we can see half of the face of the moon facing us lit up. And what do we know about that? Well, if we draw a line from this line straight back to the sun, what's that angle going to be? That's a 90-degree angle. So when we see the moon perfectly half lit, we know that the angle between us observing on the earth, looking at that perfect half lit moon, and the angle to the sun. So here's the earth. Make sure we know what we're looking at here. Here's the earth to the moon to the sun. This angle here is 90 degrees. Well, if we know that, we should be able to figure out what this distance is over here with a little bit of mathematics. So let's take a quick look at some geometry here of the earth, moon, and the sun. And let's have the earth here. Let's have a close sun. Let's put the sun really close, right about here. Sizes are not proportional. And so we know that the quarter moon is going to occur when the angle between here and there is 90 degrees. So let's go ahead and draw that moon there. So there is the angles with a close sun. So notice how small this angle is here. Let's go ahead and redraw that here. Here's the earth. Here's a distant sun. And now we're going to draw that line again. Try to get the distance just about right with the moon. And there's the line. So we know that is 90 degrees. Make our little degree symbol a little smaller. So that angle is 90 degrees, but notice with a close sun, this angle here is smaller than with a distant sun. So the further away the sun is, the more the moon is going to move toward the east before it reaches that phase of a quarter moon. So if we know that angle is 90 degrees, we can calculate the relative distance to the sun. Now, Aristarchus did not have modern trigonometry, as we know. He used Euclidean mathematics to figure it out, but he figured some ratios and stuff, and he measured this angle here. So he had to look at the moon, determine when. Let's look at this again here. Here's our moon, and we have our phases as the moon goes along. Eventually we get to the quarter moon where our angle is such that we see that line right straight there, perfectly straight line between the light side and the dark side of the moon. That's the moment of the first quarter moon. And Aristarchus measured the angle here as 87 degrees. And so with that 87-degree angle and his Euclidean math, he figured out that the sun is about 18 to 20 times the distance to the moon. So take that distance, calculate the angles, and 18 to 20 times that distance. So he was way off by more than an order of magnitude, because the sun is actually 400 times as distant as the moon. So he was off, but he got a number that showed that the sun was fairly far away. I think he was off simply because, try measuring the straightness of this line. Go out when there's a quarter moon and try to figure out when that line is perfectly straight. And all Aristarchus had was basically a ruler and his eyeball. And remember, the moon is only a half a degree across. And so he had to measure that with very crude instruments. And if he had measured it about 6 hours later, he would have gotten the more correct angle, which is just short of 90 degrees. It's only 1/6 of a degree short of 90 degrees. And then he would have gotten a correct distance to the sun. But did pretty good considering that his tools were basically a ruler and his Mark I eyeball, judging the straightness of that line to decide when to measure the angle between the sun and the moon. Got 87 degrees instead of the actual, it's something like 89.8, 1/6 of a degree short of 90 degrees. So not too bad considering what he had to work with. So what has Aristarchus given us so far? He's given us a universe with a stationary sun and a rotating Earth, a spherical Earth he already had. Now he has given us a distance to the sun, but there's more. Now let's go back to a lunar eclipse. So what are we able to tell from that? Let's look at the geometry for a moment. Here's the Earth, and here's the sun. Let me just draw a cone here. And I don't have my angles right because I don't have a big enough board for that. But remember that this is 1/2 of a degree across. And the sun is somewhere out here. We don't know how big it is or how far it is, but we do know it's 1/2 a degree across, which means that this angle will be 1/2 a degree. Aristarchus was able to calculate the distance between the Earth and the end of the Earth's shadow. And Aristarchus calculated that distance at 144 Earth radii. So in other words, we have the radius of the Earth. He calculated the distance to the end of the shadow as 144 Earth radii. I'm going to move to some modern measurements just because I want to. I'm going to work with those rather than Aristarchus's measurements. But that distance is actually 215 Earth radii. So he was off by a factor of a little less than 2. But what can that tell us? Well, if we go halfway down that shadow, so that's going to be what, 107.5 radii? Looking from the Earth, we will see that as 1/2 degree. And the width of the shadow will be 2 Earth radii here, 0 there. So here it's going to be 1 Earth radius. So at a distance of halfway across there in modern measurements, 105.7 Earth radii, that's going to be 1/2 degree in diameter. So we can do some fairly simple math and figure out how big the moon's shadow is depending on where it's falling. So if we put a card here or something, if we have a giant piece of card we can put there, the shadow of the Earth would be how big? 1/2 degree. If we put it here, I don't know off the top of my head, we have to do some calculations because we have to figure out how big is the Earth's shadow and how big does it appear because we're not right there. But we can calculate exactly how big the shadow should be in space depending on how far we are down the shadow. So let's just say that the moon comes into the eclipse. These numbers are wrong, but just to say, the moon comes in and the moon just fills the shadow, and we see that the moon is 1/2 degree in diameter. How big does that make the moon? It makes the diameter of the moon 1 Earth radius, because we determined mathematically that at that point the shadow is 1 Earth radius. So if the moon was just filled the shadow at that point, that means the Earth's diameter is 1 Earth radius, or half the diameter of the Earth. So we can calculate the size of the moon depending on where it goes through this shadow and how far away it is in reference to the diameter of the Earth or the radius of the Earth. So it turns out that the moon, let's get rid of some of these lines here. Let's redraw this part of the shadow here. So the moon comes in, and Aristarchus calculated it as 1/3 the size of the Earth. So we'll put a moon about that size right about where it fits. So if the moon is 1/3 the size of the Earth, is that about right? Let's see. Let's make it just a little bit bigger and a little closer. So the moon is 1/3 the diameter of the Earth and put there. We're kind of working backwards here. So this is what Aristarchus thought he saw, is a moon 1/3 of the Earth's diameter. And so he saw the moon enter the shadow, watched the shadow, timed it, and watched it exit the shadow and determined how big the shadow was at this point. So he determined that the width of the shadow at this point was 1.5 degrees, or 3 times the diameter of the moon, and that the moon was 1/3 of the Earth's diameter. So he calculated the moon to be mathematically right about there in the Earth's shadow. Now, he doesn't know how far this is in kilometers, or stadii as they used for measurements in those days, but he does know in relation to the size of the Earth. So he figured out that this distance between here and here was 60 Earth radii. I'll just make that as ER. 60 Earth radii. And he was spot on. I don't know how he was spot on, because he was way off on the distance between here and here, and he was off on the size of the moon too. He calculated the moon to be 1/3 the Earth's diameter, where it's really 27% of the Earth's diameter. But he did come up with the distance spot on, 60 Earth radii as the distance to the moon. So he found out the distance to the moon was 60 Earth radii. The diameter of the moon was 1/3 Earth diameter. And so, although that's wrong and the distance here is wrong, he did come up with the right measurement for the distance to the moon. So now where are we with Aristarchus? We already knew that the Earth was a sphere, and Aristarchus used the phases of the moon to calculate the distance to the sun to be about 18 to 20 times the distance of the moon. Well, he was way off, but at least he got a number that was usable. But he was spot on when he measured the distance to the moon using the eclipse. How did he do it? Once again, we could see how big the shadow was on the moon, and so he was able to calculate how big the moon was compared to that shadow, and knowing where would the shadow be that big, and calculated the distance to the moon as 60 Earth radii, and the diameter is 1/2 of, or got that wrong there, 1/3 of the Earth's diameter. So there we are with Aristarchus. We've got a round Earth that's rotating, a stationary sun so far, and seeing that the sun was 18 to 20 times further away than the moon, and they are the same size in the sky, that means that the sun is 18 to 20 times larger than the moon. And he concluded that the moon is 1/3 the size of the Earth. So you take the moon's size compared to the size of the Earth, compared to the distance of the sun, and he concluded that the sun is about 6.5 times the size of the Earth. Well, he was way off, but not doing bad considering the tools he had at the time. And we've got a distance to the sun, which is off, but we do have a distance that's much further than the moon, and a size of the sun much bigger than the Earth. Plus we got a moon that's spot on at 60 Earth radii distant, and a moon diameter of 1/3 of the Earth's diameter. So we're getting some fairly useful measurements here, although they're off, but they will be refined in the future. So that's about it for now, and in the next video we will see what Aristarchus figured out about the planets. So in the meantime, if you found this useful and informative, please give me a thumbs up down below. It really helps the channel and helps other people find these videos. And if you want to take my class in astronomy, you can see it at vocademy.net. And if you want to help me make these videos and keep Vocademy free, you can go to patreon.com/Vocademy and pledge your support. Or to make a one-time donation, you can go to paypal.me/voced, VOCED. And if you can't donate, then you can help me by subscribing to this channel, and be sure to hit the gray bell when you do so that you'll be notified when I put up new videos. And always a big thank you to my patrons at Patreon and my other donors, and thanks to everyone for watching.